Okay, so we're going to be talking about properties of functions. And we're going to learn about symmetry of functions and equations, intervals where your function is increasing or decreasing, called monotonicity, local extrema, what are the high points and low points in your graph, average rate of change, and the difference quotient. So a function is even or symmetric with respect to the y-axis if f of negative x is equal to f of x for all x in the domain of your function f, which means when you substitute in negative x into your original function, you get your original function back algebraically. And then an example of an even function that's symmetric with respect to the y-axis, as you pointed out, is x squared, because it looks the same on either side of the y-axis. A function is odd or symmetric with respect to the x-axis if, whenever you substitute in negative x for your function f, you get negative 1 times f of x. So you get the opposite of your original function. That's important. So that happens for all x in the domain of f. So here in our first definition, this is important. In our second definition, that's important because what's highlighted tells us how we check algebraically.
So what's an example for consecutive?
That's a good question. What's an example of an odd function?
The little squiggly line.
What little squiggly line?
X
X cubed. Good. X cubed. X cubed because it's symmetric with respect to the x-axis.
Yeah.
That's an example of an odd function. Okay, so now what we're going to do, you know how to identify it visually now, or how we say in math, graphically. Now what we want to do is learn how to determine this, whether a function is even, odd, or neither algebraically, which means we use the black highlighted to find that out. Okay, so let's look at the first example. Part A. So, determine if the following functions are even, odd, or neither. G of x equals x cubed we know is odd. You know it's odd, but let's actually provide the mathematical justification for it. We know it's odd, but let's write out why. So if you find g of negative x, so what we're doing is we're taking negative x. In either case, we take negative x and we substitute negative x into our function to see what we get. Do we get our original function? That would mean our function is even. Or do we get the opposite of our original function, which means our function is odd? So we substitute in negative x for x here. That gives us negative x quantity cubed. Negative x times negative x times negative x. So we're multiplying negative x times itself how many times? 3 times. So negative 1 cubed is what?
Negative 1.
Negative 1.
Negative 1. Welcome. It's negative 1, right? And x cubed is what?
Negative x.
X cubed is?
Oh, x.
X cubed. It's not a trick question. X cubed is x cubed. So you get negative 1 times x cubed, which is the same thing as negative x cubed. So notice we got the opposite of our original function, right? Which means our function is odd. And we can say it's symmetric with respect to what?
The x-axis.
And I said this wrong, so let me go back and correct this. Because symmetric with respect to the, and we'll fill in the blank here. Let me ask you a question. Is this symmetric with respect to the x-axis? No. Because if it were symmetric with respect to the x-axis, what would it look like? It would look like the first quadrant and the what quadrant?
1 and a 4.
1 and a 4th, right? It wouldn't look like that, right? It would look something like that. No, let's make sure it looks like a mirror. It's like you take this, flip it over, like that, right? But it doesn't look like that. So tell me what is symmetric with respect to?
The y-axis.
The y-axis?
To the
If-
origin.
To the origin, yeah, to the origin. So let's correct this. So this should not be the x-axis. This should be
The origin.
the origin. So let's correct that. That was a quick, let me go ahead and record for you type of thing. Okay, so let's make sure we're clear. A function is odd or symmetric with respect to the origin if f of negative x is equal to negative times f of x. What was your question?
Why that equation not even?
Because did we get our original function back?
No.
No, that's why. If we got our original function back, then our function would be even. But because we got the opposite of our original function, that means it's odd.
Basically, you just rewrite it into the rules.
You're not rewriting it into the rules. You're using negative x to figure out whether you're going to be in this rule, or neither one of these.
That's what I mean.
Yeah, that's what you're doing.
So what would it look like if it was to the x-axis, since we already have y in the origin?
But that's neither one of, so even or odd. So we only ask whether our functions, are they even or odd, and we don't ask that about the symmetric with respect to the x for this. But good question. Good question. Because right now, what you're trying to figure out is what can you say about the functions? What are the properties or the characteristics of the functions? And that's, we're trying to figure out what are the properties of functions in this section. And that's not a specific property whenever you have that symmetry about the x. What other questions do you have? Okay, good. Okay, so let's determine if this function is even, odd, or neither. What do you think it's going to be without writing it out so far? What do you think it's going to be? Even. Tell me why you think that. Say it again. We can't hear you. Because you're squaring x,
Yes.
right? You're squaring x, so if you put a negative in, your function isn't going to change. So let's write this out. So very good. So we need to test g of negative x to see what we get. So this is going to be, make sure you put that negative x in parentheses. Negative x quantity squared over 5. All of that minus 5. Negative x squared is what?
A positive.
I'm asking you to tell me what it is.
What? X squared.
X squared. Good. It's x squared. Negative x quantity squared is x squared. So this is x squared over 5 minus 5. Did we end up with our original function?
Yeah. Yes.
Yes. So this is the same thing as our original function, which means this is even and symmetric with respect to what?
Y axis.
Good. Okay, good. Take a minute and determine whether h of x equals x cubed minus 1 is even, odd, or neither. So our question is this function even, odd, or neither? And the majority voted odd. And then we had a few evens, no neithers. So let's check it. So h of negative x is equal to the quantity negative x cubed minus 1. What's negative x cubed?
Negative x cubed.
Negative 1x.
Negative x cubed
Yep.
minus what?
1.
1. Is this function the same as this function?
No.
So that tells us that h of x is what?
Not even.
So h of x is not even. Is this the opposite of our original function?
Yes. No, well.
Ask your question.
Well, because the -1 on the outside, that's why I was confused. I would have said neither, but.
And you would be correct to say neither. Because what? Say why?
Because the -1 isn't positive, so it's not opposite.
That's absolutely correct. In order for this function to be the opposite, you will have negative x cubed plus 1, right? So h of x is not odd because odd, so that is, we don't have negative times x cubed minus 1, which equals negative x cubed plus 1, right? So it's not odd, so it's not even. It's not odd. What is it? Neither. Neither. You got it. Does that make sense?
Wait,
Say it again. Let's be respectful. What?
yeah, but graph the original function like flip.
That's right. It's not symmetric about the origin, right? And if it were symmetric about the origin, then you'd be able to tell that it was odd, but it's not. So that's good. You can check in Desmos by graphing your original function on one line and then graphing this function, and you will confirm that it's neither. Okay? Very good. So, your question was, what happens whenever you asked, Alexandria asked about symmetry with respect to the x-axis? So let's go back and let's revisit that concept, okay? An equation in x and y is symmetric with respect to, and now we have several options. 1, the y-axis, if replacing x with negative x results in an equivalent equation. So in other words, if our function is what? Even, right? Symmetry with respect to the y-axis means our function is even. We're just connecting concepts. It's symmetric with respect to the x-axis. You have to read the condition. The x-axis, if replacing y with negative y, results in an equivalent equation. So notice the difference. Whenever we were checking to see if our function was even, odd, or neither, we replaced x with negative x. If you're checking for symmetry with respect to the x-axis, you're replacing y with negative y. So notice that you're using the other variable now. Okay? That's why we separate them. Okay? So, it's an equation in x and y is symmetric with respect to the what if replacing x with negative x and y with negative y results in an equivalent equation. This is origin, in which case our function is what? You got it. Okay? So, for each part of example 1, we are now going to determine if our example is symmetric with respect to the y-axis, x-axis, or origin, or none of the above. G of x equals x cubed. Symmetric with respect to the origin. You got it. Just to confirm, g of negative x equals negative x quantity cubed, which we already found was negative x cubed. So symmetric with respect to the origin. G of x we know is what for B? Can't hear you? I can't hear you at all. Our parent function is x squared, but in terms of, that's good, in terms of answering our question, respect to the what? Y-axis. Good. Symmetric with respect to the y-axis. So we find g of negative x. That's equal to negative x quantity squared over 5 minus 5, which is equal to x squared over 5 minus 5, which is our original function. It's the equivalent to our original function. So we have symmetric with respect to the y-axis. And part C, what do we know about part C?
No.
Y, is it symmetric with respect to the y-axis, x-axis, origin, or none of the above?
None of the above.
None of the above. None of the above. Good. So h of negative x is equal to negative x quantity cubed minus 1, which is negative x cubed minus 1, which is not our original function. So it's not the opposite of our original function, so none of the above. In other words, it has no symmetry. Okay?
So would that just be like a reflection? Since we know that it's like holographic, would it just be like a reflection of the y-axis?
So the question is it just a reflection? No. That's a good question though. It's not just a reflection. So if you're taking a reflection and you're asking is it a reflection about the y, that means you're taking it and then it looks like that. But that's not what happens here because it's not even. Remember, symmetric about the y-axis means your function is even. Okay? A few more definitions. This page is all about monotonicity. This page is all about monotonicity. Remember, we're choosing or determining whether our function is increasing or decreasing. So a function f is increasing on an interval if for any x1 and x2 in the interval with x1 less than x2, then f of x1 is less than f of x2. For those who are highly visual, on the axis, in the xy plane, what does that look like? We do not necessarily have to be in the first quadrant. I'm just using the first quadrant. So if you have x1, it says x1 is less than x2, so that means x1 is to the left of x2, right? Are you with me? Are you with me? Okay. Then that means f of x1 is less than f of x2. So f of x1 would be the corresponding y value and f of x2. So it would look like this, something like that.
Wait, I don't see that part.
On the screen?
No, online. The definitions online, it skips straight to example 3.
Okay, so add a page in.
Oh,
Does everyone have that?
I got it on paper, so.
You have it on paper? So something must have happened when you downloaded it.
There was one, yeah, there was one chapter that had two different ones.
Two different, what do you mean?
Like files that we have to download. One of them had less pages than the other. I just.
Which section was it?
5.2, I think. Isn't this
So
one?
that was this one?
Yeah.
Okay.
I think it was this one.
So that was me then. Did one say partial? Or did one say filled in?
It said part 1.
Part 1, that's why.
It said part 1.
That's why. Once is part 1 and the other's part 2? That's why. That's why.
Okay, I see.
Does that make, I'm glad you all asked that. I'm glad you asked that. I'm glad you all pointed that out. If there's a part 1 and part 2 to the notes, then that means I separated it in terms of covering it. Okay? Good. Okay? So, does everybody have it now? Okay. So, whenever you have x1 is less than x2, then whenever we know our function is increasing, whenever f of x1 is less than f of x2. Okay? So increasing would look like this. A function is decreasing on an interval if for any x1 and x2 in the interval with x1 less than x2, so again, you have x1 is less than x2. So again, x1 is to the left of x2. If we have that set up, then f of x1 is greater than f of x2. That would mean our function is decreasing. And that should be an x sub 2 right there. So f of x1 would be up here in this case, and this would be f of x2. That's what it means whenever you have decreasing on an interval. Okay? A function f is constant on an interval if for any x1 and x2 in the interval, then f of x1 equals f of x2. So it doesn't matter where you are on the x-axis with your x's. It doesn't matter. You can have x1 here, you can have x2 here, it doesn't matter. That means your f of x1 and your f of x2 are going to be the same. So horizontal line is what it's going to look like. That means it's constant. If f of x1 and f of x2 are the same, that means you have your function is constant. What questions do you have? Is it helpful to see the graph so you can connect the graph, connect the graph with what we're saying with the highlighted portion? Yes. Okay. Okay, so note, identifying the intervals of the x-axis for which a function f is increasing in value, decreasing in value, or remaining constant is finding the intervals on which f is monotone. Okay, remember, if you need to send a message, go in the hallway. Okay, so finding our intervals of monotonicity means we're finding the intervals on the x-axis, or we're finding our domain where our function is increasing and decreasing. Okay, so let's actually go through an example now. Let's go through an example. Okay, so example 3, determine the open intervals of monotonicity of the function f of x equals x minus 2 quantity squared minus 1. We're going to use the graph. Okay, we're going to use the graph. So, tell me what your parent function is.
X squared.
X squared, you know the shape. Tell me what shifts and compressions and what we're going to do. What are we going to do with x squared?
Right 2.
Go right 2 and then
Down 1.
down 1. So this point right here is what? 2, negative 1. Very good. 2, negative 1. Very good. And then we're going to sketch our parabola. We know it's a parabola. Okay? Very good. So, our question is, what are our intervals? Now, we've talked about intervals before, so now we're going back to graphs and identifying our domain, essentially. So we want to know when our function is decreasing and when is our function increasing. When do you think our function is decreasing? What interval? What do I mean? Where, so for what x values is our function decreasing?
2, right? Says
You're saying it's decreasing right here?
at 2, the y is negative 1.
So that's the specific point.
And one,
Negative 1.
So you're saying 2, -1 is where our function is decreasing. But if we look at our graph and you're saying that, that means we're only picking the point.
Oh, so it should just be.
They can't hear you.
I forgot what it's called. I think it's like it's an interval notation.
Yes. So right now we're going back to interval notation. So let's take a quick reminder. Okay? Let's take a quick reminder. So when I ask you when is this function decreasing, you're looking at the whole graph, right? Is this function decreasing here?
Yes.
Or is it increasing here?
it's decreasing.
It's decreasing, right? So I'm asking you for what x values is that happening? This arrow means it goes on forever to negative infinity, right?
Negative infinity.
Negative infinity to
One, two.
negative infinity to 2.
Okay.
So negative infinity to 2. So I'm going to highlight in green. This is our function decreasing. That's just making the connection that that's our function, but the corresponding x values for which is decreasing is that. So our function is doing what here?
Increasing.
Increasing. So tell me what the interval will be.
Oh, -1 to.
2 to infinity.
What goes at 2?
Bracket.
I heard bracket, I heard parentheses. So parentheses, because if you say bracket, that means you include 2. 2 to infinity, good. So then from here on out, that's where your function is increasing. Are we good? Okay, so whenever I ask this type of question, this is what I'm asking you to find now. Find the intervals where your function is increasing or decreasing. So you have to zoom in on the x-axis. A function, so there's a lot of terminology because you're now putting the terminology with parts of the graph and you're putting it with algebra. So that's why this section is like that. So what you should do, I'm taking a beat to remind you what you should be doing, putting your sheet together and reviewing these daily. That's how it sticks. Okay? All right. So a function f has a local maximum. It has a local maximum. Some people say local max. I'm okay with that too. Local maximum at C if there's an open interval AB containing C for which f of x is less than or equal to f of C for all x in that interval AB. In this case, we say f of C is the local maximum value of f. We say it's the local maximum value of f. So if you have let's look down here. If you have an open interval AB, and then it contains an element C, okay, for which f of x, no matter for what x you are here, let's use this. No matter what x you choose in this interval AB, not outside of it, inside of this interval here, the corresponding f of x value, wherever you are in this interval, it will not be higher than this value. That means this is a local max. Okay? This is the local max concept, local maximum. And note that, listen to the language. It says we have a local maximum at C, but the local maximum value is f of C. The local maximum occurs at C, but the local maximum value is f of C. Are we good? Okay. A function f has a local minimum at C if there's an open interval AB containing C for which f of x is greater than or equal to f of C for all x in the open interval. In this case, we say f of C is the what? Local minimum value. Very good. Of f. Okay, so now we're in this case. So C, again, is in your open interval AB. And no matter what value you choose outside of C, this value, f of C, is going to be the smallest in that interval. So no matter where you are, this will be the smallest. Okay, so that's your local minimum. Okay, the local maxima and minima of a function, so now we're talking about plural, if you have more than one, okay? They're called local extrema. They're called local extrema. Local extrema. Okay? All right, so let's look at example 4. Okay? So, determine the local extrema of f, and then in B, determine the values of the local extrema of f. So here, in part A, I'm asking you where do the local extrema occur? And in B, I'm asking what are the values? So let's talk about our local minima. Where are our local minima? Can you talk a little louder? You want me to zoom in? That better? So at -1, you picked out a low point. That's right. And where do you pick up another low point? I can't hear you. You said 1? 4. Good. You pick up another low point here. Good. So your local minima are occur at -1 and 4. So you're asking where do you find them? That means you're looking for your x value here. Where do your local maxima occur?
2.
At 2. Good. Anywhere else?
2 and 2.
2 and, huh?
Oh, I thought we were talking about like the coordinate.
So if you thought I was talking about the coordinate, but notice that the way I phrase these questions, I separated it. So in part A, I'm asking you for the x value. In part B, I'm asking you for the y value, right? So we identified 2 local minimum. So we should have 2 local minimum values. So the local minimum value at -1 is what? -2. Good. So that means we go to -1 and we pick up this 2. That's the value. Okay? Then the local minimum value at where? 4, good, bless you, is what? What is it? 1, good. And what else do we need to say?
Local maximum value.
Our local maximum value talk loud. At 2. I can't hear you.
It's 2.
Yeah, it's 2. Good. A local maximum value at 2 is 2. What questions do you have? Okay. All right. Good. So now let's talk about rate of change, average rate of change. So this is algebraic, and you will have seen this concept before, okay? Do one example, one part of example 5, and then I'll move to the last page, and then I'll add the other example to the recording for you, and then upload the video, and that will be the end of this section, okay? So,
It's recorded, right?
yes, yep. Do the recordings help or no?
Yes.
Okay. Given a function f defined on an interval AB where a and b are not the same, the average rate of change of f over AB is given by f of b minus f of a over b minus a. You need to know this. This formula is a formula for average rate of change. So let's apply it. For each given function and interval, determine the average rate of change of the function over the interval. Okay, so part A, we have f of x is 3x plus 17 over the interval -2, 0. What's A for us?
-2.
A is -2, and what's B? 0. Good. So, according to the formula, we have f of 0 minus f of
-2.
good, all over 0.
Minus -2.
Good. So, f of 0 means we're now going to take 0 and substitute it in for x here. So, that gives us 3 times 0 plus 17 minus the quantity. So far, this is the same thing as f of 0 minus f of -2. So now we put -2 in. We substitute -2 in for x, very good, to get 3 times -2 plus 17. So we'll be subtracting that entire quantity, and we're going to divide it by 0 minus -2, which is 2. Okay, so now we simplify. 3 times 0 is 0, good. So we have 0 plus 17 minus the quantity. 3 times -2 is -6, good. -6 plus 17 is 11, good. So minus 11 all over 2. 17 minus 11 is good. 6 over 2 is 3. That's the average rate of change of this function over this interval. That's what average rate of change is all about. Okay? And it turns out average rate of change is really the same thing as difference quotient if we change our intervals. Okay? If we change our intervals, average rate of change is the same thing as difference quotient. And we talked about difference quotient before So we're just going to revisit it here so you can connect the two concepts. Okay? So definition. The difference quotient. You remember this kind of problem?
Yes.
Okay, good. The difference quotient of f at c with increment h is the average rate of change of a function over an interval of the form c to c plus h. And if you want to use what you had before, you would do x to x plus h. Okay, so this is the formula. You got to know it. Okay, so let's determine the difference quotient for f of x equals x squared minus 3. Now before, whenever I went over this with you, we did it in steps. Would you like to do it in steps here, or would you like to do it all together? In steps? Okay, so step 1. Let's find f of c plus h. That's equal to c plus h quantity squared minus 3. Using the FOIL method, that's c plus h times the quantity c plus h minus 3. Use the FOIL method, expand, you get c squared plus 2ch plus h squared minus 3. We cannot combine any terms. Step 2, we find f of c plus h minus f of c. We found f of c plus h in our numerator, so we're just going to take what we ended with, c squared plus 2ch plus h squared minus 3, and we're going to subtract from that the quantity and what we get when we substitute in c here. When you substitute in c here, what do you get? When you substitute in c here, what do you get? What's f of c? Very good. C squared minus 3. Very good. C squared minus 3. You got it. And now you distribute your negative. So that's c squared plus 2ch plus h squared minus 3 minus c squared plus 3. Can you combine any terms? The 3's cancel out, good. And what else happens? You got it. The c squares cancel out. And we're left with 2ch plus h squared. Good. So now our third step is just taking that and dividing by h. So finding our difference quotient. So step 3 is we have f of c plus h minus f of c all over h. That's equal to 2ch plus h squared divided by h. And in the numerator, they have what in common? H's. So this is equal to h times the quantity 2c plus h all over h. And what happens? Yeah, good. They cancel and leave us with what? You got it. That's the difference quotient. That's it. And that's section 5.2. That's section 5.2. So on Thursday, we're going to go through 5.3, and then you'll have your group work. You'll go through 5.3, and you'll have your group work, and you'll have a quiz on what we had before, so 4.4 through 5.3. Okay? So your quiz is online, right? Your quiz is online. When would you like me to open that?
After Easter.
After Easter.
Y'all saying after Easter?
Y'all know Easter is like this weekend, right?
You're saying after? How about we open it Thursday?
Oh, no.
We open it Thursday.
Thursday
And you got 24 hours.
Not close to being.
Open it Friday. We don't have
So you want me to open it on Monday?
Yes.
That's fine.
I'll open it for you Monday and give you how long?
24 hours.
24 hours. Listen, make sure you remember here.
Yeah, it's Friday.
Make sure that I'm saying, make sure you remember, because this is going to be due before Tuesday.
Is 5.2 still due tomorrow?
Yeah. You have questions. If you have questions, come and find me. I got office hours today. Have a good one. Thank you.